There exists a distance in the universe that represents a true boundary, a place beyond which no information can currently reach us, no light has yet arrived, and no observation is presently possible. This distance is measured with precision. It extends approximately 46.5 billion light-years in every direction from where you are right now. It forms a sphere around Earth, around our solar system, around every point in space where an observer might exist. This boundary is real. It is measurable. Scientists have calculated its position using observations of the cosmic microwave background radiation and measurements of how the universe has expanded since its beginning. The edge is there, definite and quantifiable, marking the limit of what we call the observable universe. And yet, at the same time, the universe itself may have no edge at all. The total universe, the complete expanse of space and matter and energy, might extend infinitely in all directions, going on. Without any boundary, without any wall or limit or conclusion. The cosmos you cannot see may simply continue, repeating patterns of galaxies and vast structures, perhaps forever. These two statements, seemingly contradictory, both appear to be true based on current scientific understanding. This is not a paradox in the formal sense, not a logical impossibility, but rather a distinction between two different concepts that our everyday experience does not prepare us to separate cleanly. One boundary is a horizon of observation, determined by the finite age of the universe and the finite speed of light. The other is a question about the fundamental geometry and extent of space itself. Understanding how both can be true simultaneously requires a careful exploration of what we mean by distance, what we mean by edges, and what the universe's expansion implies for the relationship between those concepts. The observable universe has a definite size because the universe has a definite age. Current measurements indicate the universe is approximately 13.8 billion years old, dating back to what we call the Big Bang. Light travels at a fixed speed, roughly 300,000 kilometers per second, and in the age of the universe, light has had only a finite amount of time to travel. This creates a natural horizon. Any object so distant that its light has not yet had time to reach us remains beyond this horizon, invisible and unobservable, not because of any technological limitation, but because of a fundamental constraint imposed by the speed of light and the age of the cosmos. You might initially think that this horizon should be 13.8 billion light-years away, matching the age of the universe. A photon traveling for 13.8 billion years at the speed of light would cover 13.8 billion light-years of distance. But the actual calculated distance to the edge of the observable universe is much larger, approximately 46.5 billion light-years. This difference is not an error or a contradiction. It reflects something profound about the nature of space itself. Space has been expanding throughout the entire history of the universe. When a photon was emitted from a distant galaxy billions of years ago and began its journey toward us, that galaxy was much closer to our location than it is now. As the photon traveled through space, space itself was stretching, increasing the distances between all points that are not gravitationally bound together. By the time that photon reaches us today, after traveling for billions of years, the galaxy that emitted it has moved much farther away due to this expansion. The distance the light traveled in its journey is not the same as the current distance to the object that emitted it. This expansion of space is not like objects moving through space in the conventional sense. Galaxies are not racing through a pre-existing arena. Rather, the fabric of space itself is growing, carrying galaxies along with it. When we measure the distance to the edge of the observable universe, at 46.5 billion light-years, we are measuring what is called the proper distance or co-moving distance, which accounts for how much space has stretched during the time the light was traveling. This is the distance to those regions right now in a cosmological sense of simultaneity, even though the light we see from them shows how they looked billions of years ago. The edge of the observable universe is sometimes called the particle horizon. It represents the maximum distance from which light could have reached us since the beginning of the universe. Everything within this sphere is potentially observable, given sufficient time and sensitive enough instruments. Everything beyond it is not yet observable and may never become observable depending on how the universe continues to expand in the future. This horizon is not a physical structure. There are no walls, no membranes, no material boundaries at this location. It is purely a limit of information and causality. If you could somehow travel to a point near this horizon, you would not notice anything special about the local space there. You would still be surrounded by galaxies and cosmic structures, and you would have your own observable universe extending 46.5 billion light-years in all directions from your new location. This is where the concept of infinity enters. When scientists say the universe might be infinite, they are making a statement about the total extent of space itself, beyond what any observer can see. The observable universe is finite because of the limitations imposed by light speed and cosmic age. But the full universe, the entirety of existence, may extend beyond our horizon indefinitely. There may be no point where space ends, no boundary beyond which there is nothing. The galaxies we cannot see might simply continue existing in regions we can never observe from our current position in space and time. Current observations provide strong evidence supporting this possibility. Measurements of the cosmic microwave background radiation, which represents light from when the universe was only 380,000 years old, show that space is remarkably flat. In the language of geometry, this means that parallel lines remain parallel. Triangles have interior angles summing to 180 degrees, and the local curvature of space is very close to zero. A flat spatial geometry, in standard cosmological models, is consistent with an infinite extent. If space were curved in a certain way, forming something analogous to the surface of a sphere in higher dimensions, it would necessarily be finite. But measurements indicate that if any such curvature exists, it must be extremely slight, so slight that the observable universe is far too small a region to detect it. The precision of these measurements is striking. Data from satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have determined that space is flat to within about half of 1%. For the universe to have maintained this degree of flatness over its entire history of expansion, stretching from unimaginably small scales to the vast structures we observe today, the initial conditions must have been extraordinarily precise. This observation is part of what led to the development of cosmic inflation theory, which proposes a brief period of exponentially rapid expansion in the universe's earliest moments. The horizon you can see is real and measurable, a sphere extending 46.5 billion light-years in radius. Beyond it lies more universe, potentially infinite, continuing in patterns we cannot directly observe. These are not contradictory statements, but complementary truths about different aspects of cosmic structure. One describes the limits of information and observation. The other describes the possible extent of space itself. As we explore these concepts more deeply, the relationship between edges and infinity becomes clearer, revealing a universe more subtle and more magnificent than our initial intuitions might suggest. The observable universe takes the form of a sphere centered on Earth, not because Earth occupies any special position in the cosmos, but simply because that is where we are making observations. Every observer, at every location in the universe, sits at the center of their own observable sphere. These spheres overlap partially with ours if the observers are relatively nearby, or they might be completely disjoint if the observers are sufficiently distant. The shape is spherical because light travels at the same speed in all directions, and the universe has roughly the same age everywhere, creating a symmetric horizon around each observer. The radius of this sphere, approximately 46.5 billion light-years, represents the comoving distance to the most distant objects whose light can currently reach us. To understand what this means, we need to examine how cosmologists measure distance in an expanding universe, because the expansion creates subtle complications in what seems like it should be a straightforward concept. When light leaves a distant galaxy and begins traveling toward us, that light moves through space at a constant speed of approximately 299,792 kilometers per second. This speed does not change. Light does not accelerate or decelerate as it travels. However, as the light is in transit, the space through which it is traveling is itself expanding. This expansion affects the light in several ways. First, the wavelength of the light gets stretched by the expansion, an effect called cosmological redshift. Light that was emitted in the visible spectrum might be stretched so much that by the time it reaches us, it has been shifted into the infrared or even microwave portions of the spectrum. The amount of this redshift tells us how much the universe has expanded during the light's journey. A galaxy with a redshift of 2, for example, emitted its light when the universe was about 1/3 its current size. The wavelengths have been stretched to 3 times their original length. Second, the expansion affects how we calculate distances. If you could freeze the universe at a single moment in cosmological time and measure the distance to a galaxy, you would get the co-moving distance, which accounts for all the expansion that has occurred. But the light from that galaxy left when the universe was smaller, and it has been traveling through expanding space ever since. The light travel distance, the actual path length the photons traversed, is different from the current co-moving distance to the galaxy. The most distant objects we can observe are those that emitted their light shortly after the universe became transparent to radiation, an event that occurred approximately 380,000 years after the Big Bang. Before this time, the universe was filled with a hot, dense plasma of electrons and protons that scattered photons constantly. Light could not travel freely. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, photons were suddenly able to stream freely through space without scattering. This moment is called recombination or decoupling, and the light from this epoch is what we observe today as the cosmic microwave background radiation. The objects that emitted this light were, at the time of emission, only about 42 million light-years away from the region that would eventually become our location. The universe was much smaller then, compressed by a factor of about 1,092 times compared to its current size. The light from these objects has been traveling toward us for 13.8 billion years, during which time the universe has expanded enormously. The regions that emitted this light are now located approximately 46.5 billion light-years away from us. They have been carried away by the expansion of space itself. This creates the spherical boundary of the observable universe. We can see the cosmic microwave background coming from all directions, forming a shell around us. This shell represents the surface of last scattering, the point in space and time where the photons we now observe last interacted with matter before traveling freely to us. Everything beyond this shell is in principle observable through photons, though in practice we are limited by the technology and sensitivity of our instruments. Anything that emitted its light from farther away than this distance or earlier than this time is beyond our particle horizon and remains unobservable through electromagnetic radiation. The observable universe contains approximately 2 trillion galaxies according to current estimates, though this number remains uncertain and could be revised as observations improve. Each of these galaxies contains somewhere between 10 million and 1 trillion stars, depending on the galaxy's size and type. The total number of stars in the observable universe is estimated at around 10 to the 24th power, a number so vast that it exceeds the total number of grains of sand on all of Earth's beaches. Yet this entire observable universe is just a small fraction of the total universe, if the cosmos is indeed infinite, or even if it is finite, but much larger than what we can see. The edge of this observable sphere is not approaching us at the speed of light, as one might initially think. Instead, it is receding from us at approximately the speed of light, because it is determined by the expansion of space. Each year that passes, light from slightly more distant objects has time to reach us. Our observable universe is growing, expanding to include previously unobservable regions. The expansion is slow in human terms. Over the course of 1 million years, our observable universe grows by about 0.007%. But over cosmic timescales, this gradual expansion allows us to observe an ever-increasing volume of space. However, there is a subtlety here related to another type of horizon called the event horizon or cosmic event horizon. While the particle horizon defines what we can currently see, the event horizon defines what we could ever possibly see in the infinite future. Due to the accelerating expansion of the universe driven by dark energy, there are galaxies we can see now whose future light will never reach us. These galaxies are moving away from us so rapidly, and that recession speed is increasing so quickly that any light they emit today will never catch up to us, even given an infinite amount of time in the future. The cosmic event horizon is currently located at approximately 16 billion light-years away, much closer than the particle horizon. This means that most of the observable universe is actually beyond our event horizon. We can see these distant galaxies because we are observing light they emitted long ago when they were closer to us and space was expanding more slowly. But we will never see what these galaxies look like today or in the future. The images we receive will show them becoming progressively more redshifted, appearing to move more slowly, eventually freezing in time from our perspective as their light becomes infinitely stretched by expansion. This creates a strange situation where the observable universe is larger than the reachable universe. If we could travel at the speed of light starting today, there are galaxies we can currently see that we could never reach because the space between us and them is expanding faster than we could traverse it. The boundary between reachable and unreachable lies at a much smaller distance than the boundary between observable and unobservable. The universe, visible to us, is mostly already causally disconnected from us in terms of future interactions, even though we continue to receive information about its past. The sphere of light that defines our observable universe is a consequence of fundamental physical principles operating over cosmic scales. The finite speed of light, combined with the finite age of the universe and the ongoing expansion of space, creates these nested boundaries of observation and causality. Understanding these boundaries is essential to understanding how we can speak meaningfully about a universe that has edges while simultaneously being potentially infinite. The observable universe is a finite window into a possibly infinite whole, a limited view determined by how long light has had to travel and how much space has expanded during that travel time. The relationship between time and distance in an expanding universe is not what everyday experience would lead us to expect. If an object has been moving away from you for 13.8 billion years, you might naturally assume it is now 13.8 billion units of distance away, assuming constant speed. But in an expanding universe, this assumption fails because the fabric of space itself is growing. When cosmologists describe the expansion of the universe, they are describing a phenomenon fundamentally different from ordinary motion. Galaxies do have their own individual motions through space, called peculiar velocities, which can be substantial. The Milky Way and the Andromeda Galaxy, for example, are actually moving toward each other and will eventually collide despite the overall expansion of the universe. But these local motions are small compared to the recession velocities caused by cosmic expansion at large distances. The expansion of space means that the distance between any 2 points that are not gravitationally bound will increase over time, and this increase has a particular mathematical form. The rate at which any given distance grows is proportional to the distance itself. Double the distance, and you double the rate of growth. This relationship is encapsulated in Hubble's law, which states that the recession velocity of a galaxy is equal to the Hubble constant multiplied by its distance. The Hubble constant is not actually constant over cosmic time, which is why some prefer to call it the Hubble parameter, but at any given moment in the universe's history, it describes how rapidly space is expanding. Current measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec, though there is some tension between different measurement methods that has not yet been resolved. A megaparsec is about 3.26 million light-years. This means that for every 3.26 million light-years of distance between two objects, the space between them is expanding such that they recede from each other at 70 kilometers per second. For a galaxy 10 megaparsecs away, the recession velocity would be 700 kilometers per second. For a galaxy 100 megaparsecs away, 7,000 kilometers per second. As distances increase, recession velocities can exceed the speed of light. This does not violate special relativity because no object is actually moving through space faster than light. Instead, space itself is expanding, and there is no speed limit on how rapidly space can grow. A galaxy sufficiently far away will have a recession velocity greater than the speed of light simply because there is so much expanding space between us and it. For very distant galaxies, the recession velocity can be many times the speed of light. This is why light from the most distant observable regions has taken so long to reach us. The photons we observe from the surface of last scattering have been traveling toward us for 13.8 billion years, but during that time, the space between their source and our location has been expanding. The photons were always moving toward us at the speed of light in their local reference frame, but the expansion of space was working against their progress, stretching the distance they needed to traverse. Consider a photon emitted from a point in space when the universe was only 380,000 years old. At that moment, that point was approximately 42 million light-years away from the region that would eventually become our location. The photon began traveling toward us at the speed of light. But as it traveled, space continued to expand, increasing the distance to its destination. For much of the early history of the universe, the expansion was so rapid that even though the photon was moving toward us at maximum speed, the distance to us was actually increasing for a period of time. Eventually, as the expansion of the universe slowed relative to the distance the photon had already covered, it began making net progress toward us. The expansion was still happening, still working against its journey, but not quickly enough to outpace it anymore. Over billions of years, the photon continued its journey through expanding space, its wavelength being stretched by the expansion until it finally reached the location where Earth would form much later. The total travel time was 13.8 billion years, but the source of that photon is now 46.5 billion light-years away because space has expanded so much during the journey. The mathematics describing this relationship involves integrating the expansion history of the universe. The scale factor, typically denoted as a in cosmological equations, describes how much the universe has grown at any given time compared to its size at some reference point, often taken to be the present day. At earlier times, the scale factor was smaller. At the moment of decoupling, when the cosmic microwave background was emitted, the scale factor was approximately 1/1092, meaning the universe was about 1092 times smaller than it is today. The co-moving distance to an object can be calculated by integrating along the path that light takes from the object to the observer, accounting for how the scale factor changes during the journey. This integration produces the result that while the light travel time to the edge of the observable universe is 13.8 billion years, the co-moving distance is 46.5 billion light-years. The difference is entirely due to the expansion of space during the photon's transit. This has profound implications for our understanding of cosmic geometry and extent. If we consider a galaxy at the edge of our observable universe, that galaxy has its own observable universe extending 46.5 billion light-years in all directions from its location. Some of the galaxies observable from that distant galaxy's perspective would be completely beyond our observable horizon. They exist in regions of space from which light has not yet had time to reach us, even though light from them has had time to reach that distant galaxy. The total universe must therefore extend beyond what we can see. At minimum, it must include all the regions observable from any point within our observable sphere, which already guarantees it is significantly larger than just our horizon. But current evidence suggests it extends far beyond even this conservative lower bound. If cosmic inflation theory is correct, the total universe should be exponentially larger than the observable portion, possibly by factors of 10 to the 30th power or more. The expansion continues today and is actually accelerating due to dark energy. This acceleration has existed for approximately the past 5 to 7 billion years. Before that, the expansion was decelerating, slowed by the gravitational attraction of all the matter and energy in the universe. The transition from deceleration to acceleration marks a pivotal moment in cosmic history when dark energy, which remains poorly understood, began to dominate the universe's energy budget. This accelerating expansion affects the future of observability. Over time, as the expansion accelerates further, more and more galaxies will cross beyond our event horizon, forever disappearing from our potential view. In the far future, if the current acceleration continues, only the galaxies in our local gravitational group will remain observable. All other galaxies will have receded beyond the event horizon, their light unable to ever reach future observers. The observable universe of the far future will be much emptier than ours, containing fewer galaxies, less structure, less information about the cosmos as a whole. But for now, our observable universe continues to grow slowly, as light from increasingly distant regions reaches us for the first time. The edge moves outward, revealing more of the cosmos with each passing moment, a gradual unveiling of structure and history that has continued since the beginning of time. Distance in an expanding universe is not fixed. The concept becomes time-dependent, context-dependent, requiring careful specification of what we mean. But through this complexity, a coherent picture emerges of a universe where boundaries exist not as physical barriers, but as horizons of information and causality, growing and changing as space itself expands. When scientists describe the universe as flat, they are making a statement about its geometry rather than its shape in any visual sense. The term refers to how space behaves mathematically, how distances and angles relate to each other, how parallel lines and triangles work on cosmic scales. This geometric flatness has profound implications for whether the universe must have an edge or boundary. In the simplest terms, a flat space is one where the rules of Euclidean geometry hold true. If you draw a triangle on a flat surface, the interior angles sum to exactly 180 degrees. Parallel lines remain parallel forever, never converging or diverging. The shortest distance between 2 points is a straight line. These familiar properties from ordinary geometry apply universally in a flat space. But space can also be curved in ways that violate these intuitions. On the surface of a sphere, which has positive curvature, parallel lines eventually converge. If you draw a triangle on a sphere by connecting 3 points with the shortest possible paths along the surface, the interior angles sum to more than 180 degrees. The larger the triangle relative to the sphere's size, the more the angles exceed 180 degrees. If you stand on Earth's equator and walk north to the pole, then turn 90 degrees and walk back to the equator, then turn 90 degrees and return to your starting point, you will have made only 3 90-degree turns but completed a closed path. The geometry of a curved surface differs fundamentally from flat space. Similarly, space can have negative curvature, like a saddle shape or a mountain pass. In negatively curved space, parallel lines diverge from each other. Triangles have interior angles that sum to less than 180 degrees. This type of geometry is harder to visualize because we have less everyday experience with it, but it represents another way that space can differ from the flat geometry we learn about in school. Observations of the cosmic microwave background radiation have determined that the universe's spatial geometry is very close to flat. The Planck satellite, which provided the most precise measurements to date, found that the curvature parameter differs from 0 by less than half of 1%. Within the measurement uncertainties, space appears to be perfectly flat on large scales. This finding is remarkable because flatness is unstable in an expanding universe. Any small deviation from perfect flatness tends to grow over time. If the early universe had been even slightly positively curved, it should have collapsed back on itself long ago. If it had been even slightly negatively curved, the curvature should have become increasingly pronounced as space expanded. For the universe to be as flat as we observe it today, after expanding for 13.8 billion years, the initial conditions must have been extraordinarily fine-tuned. The early universe must have been flat to within 1 part in 10 to the 62nd power, or better. This is part of what is called the flatness problem in cosmology, and it was one of the motivations for developing cosmic inflation theory. Inflation proposes that the universe underwent a brief period of exponentially rapid expansion very early in its history, during the first tiny fraction of a second after the Big Bang. This expansion would have stretched any initial curvature to such enormous scales that within any observable region, including our entire observable universe, space would appear flat. It is like zooming in on a small patch of a sphere until you can no longer detect its curvature, except that inflation did this through actual expansion rather than just changing perspective. The flatness of the universe has important implications for its possible extent. In a positively curved universe, space would necessarily be finite. It would curve back on itself like the surface of a sphere does in 3 dimensions, forming what mathematicians call a closed manifold. Such a universe would have a finite volume, a definite total size, even though it would have no edge or boundary. You could travel in any direction forever and eventually return to your starting point, just as you can travel around Earth's surface without ever reaching an edge. In a flat or negatively curved universe, however, the situation is more subtle. Flatness alone does not determine whether the universe is finite or infinite. A flat universe that is simply connected, meaning it has the straightforward topology of ordinary Euclidean space, would necessarily be infinite in extent. There would be no way to make it finite without introducing curvature or creating a boundary. But flatness is consistent with certain non-trivial topologies that allow the universe to be finite while remaining flat and boundless. Consider a simple 2-dimensional example. A flat sheet of paper represents flat, infinite space in 2 dimensions. But if you take that flat sheet and connect opposite edges, first rolling it into a cylinder and then connecting the remaining opposite edges, you create a torus, a donut shape. The surface of this torus is still flat in the sense that triangles drawn on it have angles summing to 180 degrees and parallel lines remain parallel. But it is finite in extent. If you travel far enough in any direction on a torus, you return to your starting point. You have circumnavigated the space, not because you hit an edge and turned around, but because the space wraps around on itself. In 3 dimensions, there are multiple possible topologies that are flat yet finite. The 3-dimensional analog of a torus, sometimes called a 3-torus, is one possibility. There are also more exotic options like a Klein bottle or other multiply-connected spaces. In such a universe, if you looked far enough in one direction, you might see the back of your own galaxy, though it would appear as it looked billions of years ago when that light was emitted. Astronomers have searched for evidence of such non-trivial topology. If the universe were a 3-torus smaller than the observable universe, we would expect to see multiple images of the same galaxies or the same patterns in the cosmic microwave background appearing in different directions in the sky. No such patterns have been detected. Current observations are consistent with the universe being simply connected, at least on scales up to and including the entire observable universe. This suggests that if the universe has non-trivial topology, the characteristic scale must be larger than what we can see, or the topology is simply trivial and space extends infinitely. The flatness of space means that there is no geometric requirement for an edge. A curved space that closes back on itself, like the surface of a sphere, avoids having edges by virtue of its curvature. But a flat space can achieve the same edgeless property either by being infinite or by having the right topology. The observations support one of these possibilities. Either space is flat, simply connected, and infinite, or it is flat with some non-trivial topology that makes it finite but on scales much larger than we can observe. The absence of detected curvature within our observable universe does not rule out the possibility that space might be slightly curved on much larger scales. If the radius of curvature were, for example, 100 times the size of the observable universe, we would not be able to detect that curvature with current instruments. Our observable patch would appear flat, just as a small region of Earth's surface appears flat even though the planet is curved. So the universe could be finite and closed if it is sufficiently large, or it could be flat and infinite, or it could be flat and finite with non-trivial topology. Current observations cannot definitively distinguish between these possibilities. What we can say with confidence is that within the observable universe, space behaves according to flat geometry to high precision. The universe we can see has no physical edges, no boundaries where space ends. If you could travel in any direction indefinitely, you would not encounter a wall or a discontinuity. Either you would keep going forever through infinite space, or you would eventually return to your starting location after circumnavigating a finite but boundless universe. Both possibilities remain open based on current evidence, and both demonstrate that cosmic geometry does not require edges or boundaries in the conventional sense. The possibility that the universe is infinite in extent represents one of the most profound implications of modern cosmology. An infinite universe would mean that space goes on literally forever, that there is no limit to how far you could travel, that the number of galaxies and stars is not merely vast, but actually infinite. This idea challenges our intuitions in deep ways, yet it may be the simplest interpretation of available evidence. When cosmologists discuss an infinite universe, they are typically referring to spatial infinity rather than temporal infinity. The universe has a finite age of approximately 13.8 billion years. It had a beginning, which we call the Big Bang. But the spatial extent at any given moment of cosmic time could be infinite. This might sound contradictory at first. How can something that began at a finite time be infinite in size? The resolution lies in understanding that the Big Bang was not an explosion from a point into pre-existing space, but rather the beginning of space itself, occurring everywhere simultaneously. If space is infinite now, it was also infinite at earlier times, just denser. An infinite universe that has been expanding for 13.8 billion years was also infinite 1 billion years ago, and 1 million years ago, and even 1 second after the Big Bang. The density and temperature were higher at earlier times. The distance between any 2 points was smaller by a factor determined by the scale factor, but the total extent remained infinite throughout. The Big Bang happened at every point in an infinite space, not at a single location that then expanded outward. This concept strains our imagination because we naturally try to envision the universe as a whole from some external perspective, like viewing a sphere or a room. But there is no external perspective from which to view an infinite universe. If space is infinite, it has no outside. It has no center. Every point is, in a sense, the center from its own perspective. And every point has an infinite amount of space extending in all directions around it. The strongest evidence supporting infinite spatial extent comes from measurements of cosmic flatness. As discussed in the previous section, observations indicate that space has zero or very nearly zero curvature on large scales. In standard cosmological models based on general relativity, a flat universe that is simply connected must be infinite in spatial extent. There is no way to create a finite, simply connected flat space without introducing boundaries. which would violate the cosmological principle that the universe looks roughly the same in all directions. The cosmological principle, supported by the remarkable uniformity of the cosmic microwave background and the large-scale distribution of galaxies, states that the universe is homogeneous and isotropic on large scales. Homogeneous means it has the same properties at every location. Isotropic means it looks the same in every direction. These properties are observed to hold in the observable universe, and there is no reason to think they would suddenly fail beyond our horizon. If space is homogeneous and isotropic, and if it is flat, then the simplest mathematical description makes it infinite in extent. Cosmic inflation theory provides additional support for the infinity hypothesis. Inflation proposes that the universe underwent exponential expansion during a tiny fraction of the first second after the Big Bang, growing by a factor of at least 10 to the 26th power and possibly much more. This expansion would have taken any finite region and stretched it to scales far exceeding anything we can observe. Even if the universe started finite, inflation would have made it so large that we would never be able to detect its edges or global topology from within our observable horizon. Moreover, in many models of inflation, the process does not end everywhere simultaneously. While inflation stopped in the region that became our observable universe, allowing matter and energy to form in a hot, Big Bang, inflation might continue eternally in other regions. This leads to the concept of eternal inflation, where different regions stop inflating at different times, creating a multiverse of bubble universes embedded in a larger inflating space. The total extent of this inflating space would be infinite, and each bubble universe within it might itself be infinite. If the universe is infinite, several mind-bending consequences follow. First, there would be an infinite number of galaxies, stars, and planets. The observable universe contains approximately 2 trillion galaxies, but if space is infinite, this represents an infinitesimally small fraction of the total. Beyond our horizon, there would be infinite more galaxies in all directions, exhibiting the same variety of structures and compositions that we see in our observable patch. Second, in an infinite universe with finite density and temperature, any particular arrangement of matter that is possible must occur infinitely many times. This is a consequence of probability in infinite space. The number of ways atoms can be arranged is vast, but finite for any given volume. In an infinite universe, every possible arrangement would eventually repeat, appearing in countless regions scattered throughout the infinity. There would be infinite other planets similar to Earth, infinite other solar systems similar to ours, even infinite regions containing exact copies of you having identical experiences. This conclusion sounds like science fiction, but it follows logically from the premises of infinity combined with homogeneity. However, these copies would be extraordinarily far away. The typical distance between regions similar to our observable universe would be exponentially large, measured not in billions of light-years, but in numbers so vast they defy comprehension, expressed perhaps as 10 to the power of 10 to the power of some large number. These regions would be utterly unreachable and unobservable, separated from us by incomprehensible distances. Third, an infinite universe cannot have an average or total anything. We can speak meaningfully about the average density of matter within our observable universe, which is approximately 5 protons per cubic meter when averaged over large volumes. But the concept of an average density for the entire universe becomes problematic if the universe is infinite. The total mass would be infinite, the total volume would be infinite, and the ratio is not well defined without additional mathematical structure. Similar issues arise for other global quantities like total energy or total entropy. The possibility of infinity also affects how we think about the universe's beginning. If the universe is infinite now and has been expanding from an initially hot, dense state, then it was always infinite, just more compressed at earlier times. The Big Bang was not an explosion from a point, but a phase transition occurring simultaneously at every point in an infinite space. The temperature and density approached infinity as we extrapolate back toward time zero, but the spatial extent remained infinite throughout. However, some cosmologists argue that we should not take the concept of infinite spatial extent too literally. We can only make empirical observations within our observable universe, and any statements about what lies beyond are necessarily speculative. The universe could be finite, but so large that its global structure is undetectable from our location. Observations are consistent with infinity, but they do not prove it beyond doubt. Alternative models exist that avoid infinity while remaining consistent with observations. A very large but finite universe with non-trivial topology could appear flat and homogeneous within any observable region while still having finite total volume. The critical question is whether these finite models are simpler or more complicated than the infinite model. By the principle of parsimony, often called Occam's razor, we should prefer the simplest explanation consistent with observations. Whether an infinite simply connected space is simpler than a finite multiply connected space is somewhat subjective and depends on what criteria we use to judge simplicity. Currently, the observational evidence leans toward either infinite spatial extent or a finite size vastly larger than the observable universe. Either way, the total universe extends far beyond what we can see. The concept of infinity may represent the ultimate edge of human understanding, a boundary not in space, but in our ability to fully comprehend the cosmos. Whether space goes on forever or merely extends to unimaginable but finite distances, the universe reveals itself as something grander and more extensive than the limited sphere of light we can observe from our location in space and time. The observable universe has more than one type of boundary. While the particle horizon defines the limit of what we can currently observe, there are other horizons determined by different physical considerations. Each represents a different way in which information and causality are constrained by the expansion of space and the finite speed of light. Understanding these multiple horizons clarifies the relationships between edges, observation, and the structure of space-time. The particle horizon, which we have discussed extensively, is the maximum distance from which light could have traveled to reach us in the age of the universe, accounting for expansion. It currently lies at approximately 46.5 billion light-years and represents the boundary of the observable universe at this moment in cosmic time. Everything within this horizon is potentially observable given sufficient instrumental sensitivity. Everything beyond it is not yet observable because there has not been enough time for light to reach us. But consider a different question. If we emitted a light signal today, how far could it possibly travel before the accelerating expansion of the universe carried distant regions away from us so rapidly that our signal could never reach them? This defines a different type of boundary called the event horizon or cosmic event horizon. The cosmic event horizon represents the limit of what we could ever possibly influence or receive information from in the infinite future, assuming the current cosmological model remains valid indefinitely. Due to dark energy causing the universe's expansion to accelerate, the event horizon is located at a much smaller distance than the particle horizon. Current calculations place it at approximately 16 to 18 billion light-years from us, depending on the exact parameters used. This means that galaxies currently closer than this distance could eventually receive light we emit today, given enough time. But galaxies currently beyond this event horizon can never receive signals we send now, no matter how long we wait, because the space between us and them is expanding faster than light can traverse it. The event horizon and particle horizon will evolve differently over time. As the universe ages, the particle horizon will continue to grow, albeit slowly, as light from increasingly distant regions reaches us for the first time. We will be able to observe more of the cosmos as time passes, at least for a while. But the event horizon will eventually stop growing and may even shrink slightly before stabilizing at a maximum value, as dark energy's influence becomes increasingly dominant. This creates a peculiar situation where the region we can observe expands while the region we can interact with contracts. Most of the galaxies we can currently see are already beyond the event horizon. We observe them as they were billions of years ago when they were closer to us. Light from their past has reached us, but light they emit now or in the future will never arrive. From our perspective, these galaxies will appear to slow down, redden, and freeze in time as their light becomes increasingly stretched by expansion. We will continue to receive information from them, but that information will be increasingly delayed and redshifted, representing earlier and earlier moments in their history relative to our time frame, asymptotically approaching some final moment beyond which we can receive no further information. Another important boundary is the surface of last scattering, which corresponds to the cosmic microwave background radiation. This surface represents the shell in space-time from which the oldest photons we can observe were emitted approximately 380,000 years after the Big Bang, when the universe first became transparent to light. Before this time, photons were constantly scattered by free electrons, and the universe was opaque. We cannot observe anything before recombination using electromagnetic radiation because photons from earlier times were trapped in the hot plasma. The surface of last scattering is not the absolute edge of the observable universe because neutrinos and gravitational waves can travel through opaque matter. Neutrinos became free to stream through the universe about 1 second after the Big Bang, when the temperature dropped below 10 billion degrees. In principle, if we could detect these primordial neutrinos, called the cosmic neutrino background, we could observe even earlier times. The neutrino horizon would extend slightly farther than the photon horizon, represented by the cosmic microwave background. Similarly, gravitational waves have been traveling freely through the universe since the moment space and time began. Unlike electromagnetic radiation and neutrinos, gravitational waves do not interact with matter except under extreme conditions. A cosmic gravitational wave background should exist, carrying information from the earliest moments of the Big Bang, potentially from the inflationary epoch itself. Detecting this primordial gravitational wave background would allow us to observe the universe at earlier times than any other method, essentially pushing our observational horizon back to the very beginning of space and time. These different horizons based on different types of radiation or particles demonstrate that the edge of the observable universe is not a single monolithic boundary, but rather a collection of overlapping horizons defined by different physical processes. Each type of particle or wave that can carry information from the early universe defines its own horizon, based on when it last scattered or when it began free streaming. The photon horizon is the most accessible to current technology, but it is not the ultimate limit of what could in principle be observed. There is also a distinction between the Hubble horizon and the particle horizon. The Hubble horizon, sometimes called the Hubble sphere, is the distance at which the recession velocity due to expansion equals the speed of light. Its radius is simply the speed of light divided by the Hubble parameter, which works out to approximately 14 billion light-years with current values. Objects beyond the Hubble sphere are receding from us faster than light due to the expansion of space. The Hubble horizon is often confused with the particle horizon, but they are different. The particle horizon is larger than the Hubble horizon in our current epoch. This is because light can reach us from objects that are receding faster than light, provided that light was emitted when the object was closer and the expansion was slower. As the photons travel toward us, they are working against the expansion, but they can still make progress as long as the expansion rate is decreasing or not increasing too rapidly. In the early universe dominated by matter or radiation, the particle horizon grew faster than the Hubble horizon. But in the current era dominated by dark energy and accelerating expansion, the situation is more complex. Each of these horizons represents a boundary of information or causality rather than a physical edge. Space does not end at any of these locations. There are no walls, no transitions to different conditions, no observable discontinuities if you could somehow reach these distances. The horizons exist purely as limits imposed by the finite speed of light, the finite age of the universe, and the dynamics of cosmic expansion. They are features of our observational relationship to the cosmos rather than features of space itself. Understanding these multiple horizons clarifies what we mean when we say the universe has an edge. The edge is not in space, but in space-time, defined by light cones and causal structure. Different types of signals define different edges, all nested within each other, forming a complex web of boundaries that delimit observation and causality. Beyond all these horizons lies more universe, potentially infinite in extent, continuing with the same types of structures and physical laws that govern the space we can observe. The boundaries are real and measurable, yet they do not limit the universe itself, only our knowledge of it. Cosmic inflation theory, developed primarily in the 1980s, proposes that the universe underwent a brief period of exponentially rapid expansion during its earliest moments. This expansion occurred in the first tiny fraction of a second after the Big Bang, lasting perhaps only 10 to the negative 34 seconds or so. But during this infinitesimally short time, space expanded by an enormous factor. The exact amount of expansion depends on the specific inflation model, but typical estimates suggest the universe grew by at least a factor of 10 to the 26th power, and possibly much more, perhaps 10 to the 50th power or even greater. This exponential expansion solves several problems that plagued earlier versions of Big Bang cosmology. Before inflation theory, cosmologists struggled to explain why the universe appears so uniform on large scales when regions separated by large distances should never have been in causal contact. The cosmic microwave background shows the same temperature to within 1 part in 100,000 in all directions across the sky. Yet according to standard Big Bang theory without inflation, regions on opposite sides of the sky should never have been able to exchange information or come to equilibrium. This is called the horizon problem. Inflation solves this by proposing that all the regions we can currently observe were originally contained in a tiny volume much smaller than the scale set by light travel. time in the very early universe. Within this tiny volume, which might have been smaller than a proton, all regions were in causal contact and could reach thermal equilibrium. Then inflation stretched this tiny equilibrated region to enormous scales, far larger than what we can observe today. The uniform temperature we see across the cosmic microwave background reflects the equilibrium that was established before inflation stretched everything apart. Similarly, inflation explains the flatness of space. Any initial curvature, whether positive or negative, would have been stretched to such enormous scales by inflation that within any observable region, space would appear essentially flat. This is analogous to how the surface of the Earth appears flat when you only look at a small patch, even though the surface is actually curved. Inflation stretched space so much that any curvature that might have existed is now far beyond our observable horizon. The mechanism driving inflation is thought to involve a scalar field called the inflaton field, which created a form of vacuum energy or dark energy in the very early universe. This vacuum energy produced a strong repulsive gravitational effect, causing space to expand exponentially. Eventually, the inflaton field decayed or transitioned to a lower energy state, and the energy that had been driving inflation was converted into ordinary matter and radiation in a process called reheating. This marked the end of inflation and the beginning of the hot Big Bang phase that we more conventionally associate with the universe's early history. The implications of inflation for the total size of the universe are profound. If inflation stretched a microscopic region to encompass our entire observable universe, then the total universe must be vastly larger than what we can see. The region that inflated to become our observable universe was just one small patch in what was presumably a much larger inflating space. The total universe would extend far beyond our horizon, possibly including many regions that underwent similar inflation and reheating, but are forever beyond our observation. In the simplest inflation models, the total size of the post-inflation universe is exponentially larger than the observable universe. If inflation involved 60 e-folds of expansion, meaning the scale factor increased by e to the 60th power, or about 10 to the 26th power, then the total universe would be at least 10 to the 26th times the size of the observable universe. This is already an incomprehensibly large factor. The volume would be larger by the cube of this factor, which is approximately 10 to the 78th power times larger than our observable universe. Such a universe would be finite, but so vast that the entire observable universe would be an utterly negligible fraction of the whole. Some inflation models predict even more extreme expansion. If inflation lasted slightly longer or proceeded slightly faster, the expansion factor could be 10 to the 50 power or even greater. The total universe could then be 10 to the 150 power times larger in volume than what we observe. These numbers rapidly become meaningless in human terms because we have no intuition for such scales. Moreover, many inflation models lead to eternal inflation. In these scenarios, inflation does not end everywhere at the same time. Instead, quantum fluctuations in the inflaton field cause some regions to stop inflating while others continue. The regions that stop inflating undergo reheating and evolve into pocket universes like ours, filled with matter, radiation, and structure. The regions that continue inflating keep expanding exponentially, and within them, more regions eventually stop inflating and form new pocket universes. This process continues indefinitely into the future, producing an infinite number of separate pocket universes embedded in an eternally inflating background. Each pocket universe would have its own Big Bang its own observable portion, and its own evolution. The physical constants and laws might vary between pocket universes if the vacuum state that emerges after inflation can take different forms in different regions. This leads to the concept of a multiverse, where our entire observable universe is just one bubble in an infinite foam of universes, each potentially having different properties. The pocket universes in eternal inflation are causally disconnected from each other by the rapidly expanding space between them. No signal can travel from one pocket universe to another because the intervening space is expanding faster than light can traverse it. This means that the other pocket universes, if they exist, are fundamentally unobservable from our location. They lie beyond any possible horizon, not just beyond what we can currently see, but beyond what we could ever see given infinite time and perfect instruments. This creates a profound epistemological challenge. If inflation correctly describes the universe's early history, then most of the universe may be forever beyond our observational reach. We can study the physics operating within our observable universe. We can test theories against observations within our horizon, but we cannot directly verify what lies beyond. The total extent of space, the global structure of the cosmos, and the existence of other pocket universes are questions that may not admit empirical answers. However, inflation theory does make predictions that can be tested observationally, even if we cannot observe the total universe. Inflation predicts a particular spectrum of density fluctuations that should be imprinted in the cosmic microwave background. These predictions have been confirmed to high precision by satellite observations. Inflation also predicts the flatness of space, the lack of certain exotic relics like magnetic monopoles, and the existence of primordial gravitational waves with specific properties. Some of these predictions remain to be verified, but the theory's track record gives it strong support within the cosmological community. Despite this support, inflation remains somewhat controversial because the specific mechanism remains uncertain. There are hundreds of different inflation models, each proposing different forms for the inflaton field and its potential energy function. Observations have ruled out some models, but cannot yet distinguish between many others. The fundamental origin of the inflaton field within a more complete theory of physics is unknown. String theory and quantum gravity might eventually provide a deeper explanation, but these theories remain speculative and untested at the energy scales where inflation would have occurred. Whether or not inflation is the correct explanation for the universe's early history, current observations strongly suggest that the total universe extends far beyond what we can see. The uniformity, flatness, and large-scale structure of the observable universe all point toward a cosmos of vastly greater extent than our horizon encompasses. Inflation provides one theoretical framework for understanding this greater extent and explaining how it came to be, but the essential conclusion that we observe only a small fraction of the total universe holds regardless of the specific mechanism that created it. The unknowable beyond remains one of the deepest mysteries in cosmology. We can calculate how much space inflation would have created. We can estimate minimum sizes for the total universe based on constraints from topology searches, but we cannot observe beyond our horizon. The edge of the observable universe marks the limit of empirical science in a fundamental sense. Everything beyond is inference, extrapolation, and mathematical modeling rather than direct observation. The universe may be infinite, or it may be finite, but unimaginably large, or it may have exotic, global structure we have not imagined. The answers lie beyond the boundaries of light and time. The topology of space refers to how different regions connect to each other, which can be distinct from the local geometry that describes curvature. Two spaces can have the same local geometry but different global topology, leading to different overall structures even though locally they appear identical. This distinction becomes crucial when considering whether the universe could be finite yet have no edges. Consider again the two-dimensional example of a flat sheet of paper and a flat torus. Locally, at any point on either surface, the geometry is identical. Triangles have interior angles summing to 180 degrees. Parallel lines remain parallel. Measurements of curvature yield 0. But the global structure differs dramatically. The sheet extends infinitely in two directions, while the torus has finite area and wraps around on itself. An ant walking on either walking surface would not immediately notice which it was on based on local measurements, but if it traveled far enough, it would eventually detect the difference. On the infinite sheet, it could walk forever without returning to its starting point. On the torus, it would eventually circumnavigate the space and arrive back where it began. In 3 dimensions, the possibilities become more complex and harder to visualize. The simplest flat topology is ordinary Euclidean space, infinite and simply connected. But there are 17 distinct classes of compact, flat 3-dimensional topologies, each representing a different way space could be flat everywhere, yet finite in extent. These include 3-dimensional analogues of the torus, cylinders wrapped in various ways, twisted spaces, and more exotic configurations. One particularly interesting topology is the 3 torus, which can be constructed conceptually by taking a cube of space and identifying opposite faces. If you exit through one face, you re-enter through the opposite face. This is flat because locally the space is ordinary Euclidean geometry, but globally it wraps around, creating a finite volume with no boundary. If the universe were a 3 torus smaller than the observable universe, we would expect to see certain patterns. Looking in opposite directions, we might see the same structures, though the light would have taken different paths to reach us and would show those structures at different ages. The Klein bottle represents another exotic possibility. In 2 dimensions, a Klein bottle is a surface that can be constructed by taking a cylinder and connecting the ends with a twist so that the inside and outside become connected. A 3-dimensional Klein bottle would be similar but harder to visualize without leaving ordinary 3-dimensional space. Like the torus, a Klein bottle is flat everywhere locally, but has finite volume and no boundary. Searches for non-trivial topology involve looking for specific patterns in the cosmic microwave background. If the universe was smaller than the observable universe and had a toroidal or other multiply-connected topology, we should see repeated patterns or matching structures in different directions of the sky. The same physical structures would appear in multiple locations because light from them would have taken different paths around the universe to reach us, wrapping through the topology. Observations from satellites such as the Wilkinson Microwave Anisotropy Probe and Planck have searched for these patterns extensively. The analysis involves looking for correlations in the temperature fluctuations of the cosmic microwave background at large angular scales. If the universe had the topology of a 3 torus with a fundamental domain smaller than the observable universe, we would expect to see specific types of correlations that do not appear in an infinite, simply connected space. The searchers have found no evidence for such patterns. This places lower limits on how small a multiply-connected universe could be. For a cubic 3 torus, observations indicate that the side length must be at least 80% of the observable universe radius and likely much larger. More recent analyses from 2024 suggest that while simple 3 torus topologies with characteristic scales smaller than the observable universe are ruled out, more exotic twisted topologies might still be possible even at relatively small scales. These include versions of the 3 torus with rotational identifications that would produce more subtle patterns in the cosmic microwave background. The concept of a hall of mirrors provides an intuitive way to think about multiply connected topologies. If you were in a room where opposite walls were perfect mirrors, you would see infinite copies of yourself extending in all directions. A multiply connected universe works similarly in 3 dimensions. Light from distant objects would take different paths around the topology, arriving from multiple directions and creating the appearance of multiple copies of the same structures distributed across the sky. In principle, you could even see the back of your own galaxy by looking far enough in one direction, though the light would show the galaxy as it appeared billions of years ago. For a multiply connected topology to remain undetected, it must either have a characteristic scale much larger than the observable universe, or it must be of a type that produces patterns too subtle for current observations to detect. The latter possibility has gained renewed attention, with recent studies showing that certain twisted versions of flat topologies can evade detection more effectively than previously thought. These topologies involve connections between different regions that include rotations, making the matching patterns in the cosmic microwave background less obvious. The distinction between local geometry and global topology is crucial. Here, local geometry tells us how space curves at each point and determines how light travels on short distances and how gravity works. Topology tells us how space connects to itself over large distances and determines whether you can travel in a straight line and eventually return to your starting point. 2 universes can have identical local geometry everywhere, yet have completely different global structures. A flat, infinite space and a flat, finite torus have the same local geometry but radically different topologies. This distinction also affects how we think about infinity. A simply connected flat universe must be infinite in extent. There is no way to make it finite without introducing curvature or boundaries. But a multiply connected flat universe can be finite even though it is flat everywhere. The finite volume comes from the topology rather than from curvature. The space wraps around on itself through identifications that connect distant regions, creating a closed structure despite having zero curvature everywhere. Current cosmological observations cannot definitively determine whether the universe is infinite or finite, but very large. Both possibilities remain consistent with all available data. An infinite simply connected flat space is perhaps the simplest interpretation of the observed flatness, requiring no additional structure beyond standard Euclidean geometry extending forever. But finite multiply connected spaces with the right topology can also explain the observations and offer the conceptual advantage of avoiding the infinities that sometimes complicate theoretical discussions. The search for cosmic topology continues as observational capabilities improve. Future surveys of the cosmic microwave background with higher sensitivity and resolution may be able to detect more subtle patterns that would indicate non-trivial topology. Observations of the large-scale distribution of galaxies can also constrain topology through different methods, looking for patterns in how structures cluster and align across vast distances. The question may eventually find a definitive answer, or it may remain one of the fundamental unknowables about our universe, a property of the cosmos that extends beyond our observational horizon. Understanding how space connects helps clarify how the universe can have boundaries in observation while being boundless in structure. The observable universe has a definite edge determined by the finite age of the cosmos and the speed of light. But the total universe, whether infinite in the standard sense or finite with multiply-connected topology, has no such edge. Space continues beyond what we can see, and whether it continues infinitely or curves back on itself through topological connections, it does not end. There are no walls, no barriers, no points where space stops existing. The geometry and topology work together to create a cosmos that can be explored without limit, even if only a finite portion of it can ever be observed from any given location. The universe's expansion is not slowing down as gravity would naturally cause it to do. Instead, observations made in 1998 revealed that the expansion is accelerating, increasing its rate over time. This acceleration implies the existence of something pervading all of space that exerts a kind of repulsive gravitational effect, pushing everything apart. Scientists call this mysterious component dark energy, though that name simply acknowledges our lack of understanding about what it actually is. Dark energy comprises approximately 68% of the total energy content of the universe, making it the dominant component in the cosmic inventory. Ordinary matter, including all the atoms that make up stars, planets, and living things, accounts for only about 4% of the total. Dark matter, which interacts primarily through gravity and makes up the scaffolding around which galaxies form, contributes about 27%. The remaining small fraction consists of radiation in the form of photons and neutrinos. That dark energy constitutes more than 2/3 of everything in the cosmos is remarkable, given that we know almost nothing about its fundamental nature. The discovery of cosmic acceleration came from observations of type Ia supernovae, which serve as standard candles for measuring cosmic distances. These supernovae occur when a white dwarf star in a binary system accretes matter from its companion until it reaches a critical mass of approximately 1.4 solar masses, triggering a thermonuclear explosion. Because this critical mass is always the same, all type Ia supernovae have roughly the same intrinsic brightness. Astronomers can measure their apparent brightness as seen from Earth and use that to calculate their distance. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, compared the distances to distant type Ia supernovae with their redshifts, which measure how much the universe has expanded since the light was emitted. They found that the distant supernovae were systematically fainter than expected, meaning they were farther away than standard cosmological models predicted. This could only be explained if the expansion of the universe had been accelerating, carrying the supernovae to greater distances than they would have reached if expansion were decelerating or constant. The finding was unexpected. Prior to this, most cosmologists assumed that the mutual gravitational attraction of all the matter and energy in the universe would slow the expansion over time. The rate of slowing would depend on the total density of matter and energy, with denser universes decelerating more rapidly. An open universe with low density would expand forever, but with decreasing velocity. A flat, critical density universe would asymptotically approach a state of zero expansion rate. A closed, high-density universe would eventually stop expanding and recollapse into a big crunch. All these scenarios involve deceleration, not acceleration. The observation that expansion is instead speeding up required introducing a new component into cosmological models. This component needed to have negative pressure, meaning it would exert a repulsive rather than attractive gravitational effect. In general relativity, pressure contributes to gravity, and negative pressure produces repulsive gravity. This is counterintuitive because in everyday experience, pressure and gravity are unrelated. But in the framework of Einstein's equations, energy density and pressure both affect space-time curvature, and the combination determines whether gravity attracts or repels. The accelerated expansion began approximately 9 billion years after the Big Bang. Before that, the expansion was decelerating as expected, slowed by the gravitational attraction of matter. But as the universe expanded, the density of matter decreased. The amount of matter per unit volume dropped as space grew larger, diluting the matter content. Dark energy, however, maintained constant density as space expanded. If dark energy is indeed a property of space itself, then as more space comes into existence through expansion, more dark energy appears to fill that space, keeping the density constant. Eventually, the density of matter dropped to the point where dark energy became the dominant component, and its repulsive effect began to overcome the attractive gravity of matter. This marked the transition from deceleration to acceleration. Since then, the expansion has been speeding up, and the acceleration continues to increase as dark energy becomes ever more dominant relative to the diminishing density of matter. This transition, approximately 5 to 7 billion years ago, represents a pivotal moment in cosmic history, changing the universe's trajectory from one that might eventually slow to a halt to one that will expand forever at an accelerating rate. The nature of dark energy remains one of the deepest mysteries in physics. The leading candidate is the cosmological constant, a term that Albert Einstein introduced into his equations of general relativity in 1917. Einstein originally included the cosmological constant to balance gravity and create a static universe, but when Edwin Hubble later confirmed that the universe was expanding, Einstein removed the constant, reportedly calling it his greatest blunder. But the discovery of accelerating expansion rehabilitated the cosmological constant concept, giving it a new purpose as a description of dark energy. If dark energy is a cosmological constant, it represents the energy density of empty space itself, often called vacuum energy. Quantum field theory predicts that empty space is not truly empty, but filled with quantum fluctuations, with particle-antiparticle pairs constantly appearing and disappearing. These virtual particles exist for only tiny fractions of a second, allowed by the uncertainty principle in quantum mechanics, but during their brief existence, they contribute energy to the vacuum. This vacuum energy would have the properties needed for dark energy, maintaining constant density as space expands and exerting negative pressure. However, there is a severe problem with this interpretation. When physicists calculate how much vacuum energy should exist based on quantum field theory, the result is over 100 orders of magnitude larger than the observed value of dark energy. This enormous discrepancy is called the cosmological constant problem. If quantum vacuum energy were as large as theory predicts, the universe would have expanded so rapidly that no structures could have formed. The fact that galaxies and stars exist at all means the actual value must be far smaller than the theoretical prediction. Why the two values differ by such an enormous factor is completely unexplained. This has led some researchers to explore alternative explanations for dark energy. One possibility is quintessence, a dynamic scalar field that varies in space and time rather than being constant like the cosmological constant. Quintessence could have changed its strength over cosmic history and might continue to change in the future. Different quintessence models predict different behaviors for how dark energy evolves, and future observations might be able to distinguish between these models and a true cosmological constant by measuring very precisely how the expansion rate has changed over time. Recent data from the Dark Energy Spectroscopic Instrument has suggested that dark energy might not be constant, but may have varied over cosmic history, though these results are preliminary and require confirmation. If dark energy is indeed time-varying, this would rule out a simple cosmological constant and point toward quintessence or some other dynamic explanation. The implications would be profound, potentially offering clues about the fundamental physics underlying dark energy. Another possibility is that our theory of gravity itself is incorrect on very large scales. Perhaps general relativity, which has been tested extensively in the solar system and in binary star systems, breaks down when applied to distances of billions of light years. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy by proposing that gravitational attraction weakens or behaves differently on cosmological scales. However, the detection of gravitational waves from merging neutron stars has ruled out many modified gravity theories, because the gravitational waves arrived at Earth at almost exactly the same time as light from the same event, constraining how much gravity can differ from general relativity. The accelerating expansion has profound implications for the universe's future. Galaxies are currently moving apart at a rate such that their separation increases by about 0.007% every million years. This rate will continue to increase. As dark energy becomes ever more dominant, the acceleration will grow stronger. Galaxies beyond our local gravitational group will recede faster and faster, eventually crossing beyond the cosmic event horizon and disappearing from view. In the far future, if acceleration continues indefinitely, only the galaxies bound together in our local group will remain visible. The Milky Way, Andromeda, and the several dozen smaller galaxies gravitationally bound to them will eventually merge into a single large galaxy. But all other galaxies will have receded beyond the event horizon. Their light will become infinitely redshifted, making them invisible. Future astronomers living trillions of years from now would see a universe consisting of one large galaxy surrounded by empty darkness, with no evidence that other galaxies ever existed. The concept of the event horizon becomes increasingly important in an accelerating universe. While our particle horizon continues to grow slowly as light from more distant regions reaches us, the event horizon represents a shrinking boundary of reachability. Galaxies that cross beyond the event horizon are lost to us forever. We can still see them for a time, observing light emitted in the past, but we can never receive information about their current state, and nothing we do can ever affect them. The distance to this horizon depends on the strength of dark energy and the rate of acceleration. If dark energy continues to behave as observations suggest, the event horizon will stabilize at approximately 16 to 18 billion light-years. This creates the strange situation where most of the currently observable universe, which extends to 46.5 billion light-years, lies beyond our event horizon. We can see these regions because we are viewing them in the distant past when they were closer, but we will never see how they evolve beyond a certain point in their history. Their images will appear to slow down, freeze, and fade away as their light becomes increasingly redshifted toward infinite wavelengths. Some cosmological models propose more exotic behaviors for dark energy. Phantom energy is a hypothetical form of dark energy with even stronger repulsive effects than a cosmological constant. If dark energy has the properties of phantom energy, it could lead to a scenario called the Big Rip, where the universe ends in finite time as dark energy grows so strong that it tears apart all structures, from galaxy clusters down to atoms and eventually space-time itself. For certain parameter values, this Big Rip could occur in approximately 20 billion years or so. However, current observations do not favor phantom energy, and a cosmological constant or quintessence with more moderate properties seems more likely. The mystery of dark energy connects deeply to the question of cosmic boundaries and extent. Dark energy determines the future evolution of the event horizon and thus the total amount of the universe that any observer could ever access, even given infinite time. It affects how the observable universe grows or shrinks over cosmic timescales. Understanding dark energy is essential to understanding the ultimate fate of the cosmos and the nature of space itself. Yet despite decades of research and increasingly precise observations, dark energy remains fundamentally mysterious, a placeholder term for something we can measure but cannot explain. The question of whether the universe is infinite or finite represents a fundamental challenge in cosmology because it may not be answerable through observation. No matter how powerful our instruments become, we can only observe regions from which light has had time to reach us since the beginning. The portion beyond our horizon remains inaccessible, and if the universe is significantly larger than the observable portion, we may never be able to determine its true extent or global structure. This limitation is not technological, but fundamental. It arises from the finite speed of light combined with the finite age of the universe and the ongoing expansion of space. Even if we could build telescopes with unlimited sensitivity and resolution, we could not see beyond the particle horizon because light from those regions has not yet arrived. Even given infinite time to observe, we could not see beyond the event horizon because space is expanding too rapidly for light from those regions to ever reach us in the future. Current observations can tell us that the universe is at least as large as the observable portion, and they suggest it is likely much larger. The measured flatness of space, the absence of detectable non-trivial topology, and the predictions of inflation theory all point toward a total universe vastly exceeding what we can see. But these are indirect inferences based on theoretical models and their implications. They do not constitute direct observation of regions beyond our horizon. The cosmic microwave background provides our deepest observational probe of the universe's structure. This radiation, emitted approximately 380,000 years after the Big Bang when the universe first became transparent, carries imprints of conditions at that early time. The patterns in the temperature fluctuations encode information about the density, composition, and geometry of the universe. Precise measurements from satellites such as Planck have determined cosmological parameters to remarkable accuracy, confirming that space is flat to within 0.5%. This flatness, if exact, implies either infinite extent or very large but finite extent with non-trivial topology. If the universe were closed with positive curvature, we could in principle determine its total size by measuring the curvature precisely enough. But the measured flatness prevents this. We can place lower limits on how large a closed universe must be based on how flat it appears, but we cannot determine an upper limit. The universe could be barely large enough to encompass the observable portion, or it could be exponentially larger, or it could be infinite. All these possibilities are consistent with a measured curvature of 0. Searches for repeating patterns in the cosmic microwave background have found no evidence of multiply-connected topology on scales up to and including the entire observable universe. This places constraints on certain types of topology, but does not rule out all possibilities. More exotic topologies might produce patterns too subtle to detect with current observations, or the characteristic scale of any non-trivial topology might be much larger than the observable universe, making its effects undetectable regardless of observational precision. Theoretical considerations provide some guidance. Inflation theory predicts that the total universe should be enormously larger than the observable portion, perhaps by factors of 10 to the 30th power or more, depending on how long inflation lasted. If inflation is correct, then the universe extends far beyond what we can observe, and the question becomes not whether the total universe is much larger than the observable universe, but whether it is finite or infinite on these vastly larger scales. In eternal inflation models, the universe is unambiguously infinite. The inflating space contains an infinite number of bubble universes, each potentially infinite itself, depending on its local geometry. Our observable universe would be a tiny patch within one such bubble, and the vast majority of existence would lie forever beyond our observation. This scenario makes definitive statements about infinity, but it remains unverified because the other bubble universes are by definition unobservable. Some cosmologists argue that the question of whether the universe is infinite is not scientific if it cannot be tested observationally. Science proceeds by forming hypotheses and testing them against empirical data. A hypothesis that makes no testable predictions or whose key predictions lie beyond the observable horizon falls outside the realm of empirical science into philosophy or mathematics. By this standard, claims about the total extent of the universe beyond what can ever be observed are metaphysical rather than scientific. Others counter that the question has scientific content even if it cannot be directly tested. The models we use to describe the observable universe have implications for the unobservable regions. If our best models, tested against all available observations within our horizon, predict that space extends infinitely, then we have scientific reason to believe in that infinity, even though we cannot directly verify it. The alternative is to reject the models whenever they make predictions about unobservable regions which would undermine their explanatory power for the regions we can observe. This debate touches on deep questions about the nature of scientific knowledge and explanation. Can we claim to know something scientifically if it is in principle impossible to test? Does a theory have explanatory power for unobservable regions, or should we remain agnostic about what lies beyond observation? There are no universally accepted answers to these questions, and cosmologists hold different views about how to approach the boundary between the observable and the unobservable. What can be stated definitively is that the observable universe has a measurable extent of approximately 46.5 billion light-years in radius. Within this sphere, we can make observations, test theories, and constrain cosmological parameters. The geometry within this region appears flat, the matter and energy content can be measured, and the history of expansion can be reconstructed from various observations. These are empirical facts established through careful measurement and analysis. Beyond this observable sphere lies unknown territory. The total universe may extend far beyond what we can see, perhaps infinitely far, or it may wrap around on itself through multiply-connected topology, making it finite but boundless. The geometry might eventually curve on scales too large for us to detect, or it might remain flat forever. Different possibilities remain open, and current observations cannot definitively distinguish between them. The question becomes not whether the universe has an edge or is infinite, but whether we can know which is true. The observable universe definitely has an edge, a horizon beyond which we cannot see. The total universe may or may not have an edge, but if it does, that edge lies beyond our observational access. The universe we can observe appears consistent with being embedded in a much larger or infinite whole, but we cannot verify this directly. This situation is philosophically interesting but scientifically frustrating. We can describe mathematically what it would mean for space to extend infinitely. We can calculate the consequences of various topologies and geometries. We can construct models that explain all observations and make predictions about what should exist beyond our horizon. But we cannot point telescopes in that direction and verify the predictions, because those regions are and will always remain unobservable from our location in space and time. Future observations may narrow the range of possibilities. More precise measurements of cosmic geometry might detect subtle curvature that current instruments cannot resolve. Better searches for topological patterns might reveal evidence of multiply connected space. Improved understanding of inflation might constrain how large the total universe must be relative to the observable portion. But unless something unexpected changes our understanding of fundamental physics, there will likely always remain aspects of the universe's total extent and structure that lie beyond empirical verification. The mystery of measurement in cosmology thus becomes the recognition that there are questions we can ask but may never be able to answer with certainty. The universe's total extent is one such question. We can narrow the possibilities, constrain the parameters, and rule out some scenarios. But the final answer about whether space goes on forever or curves back on itself somewhere far beyond our horizon may remain unknown. The observable universe, with its definite boundaries of information and causality, may be all we can ever truly know about the cosmos as a whole. The universe contains two truths that initially seem to contradict each other, but are in fact complementary descriptions of different aspects of cosmic structure. The observable universe has a definite edge, a measurable boundary, approximately 46.5 billion light-years away in all directions, marking the limit of regions from which light has had time to reach us. This edge is real and quantifiable, determined by the finite age of the universe and the finite speed of light working within the framework of expanding space. At the same time, the total universe, the complete expanse of space and everything within it, may have no edge at all. Current evidence suggests that space extends far beyond what we can observe, perhaps infinitely far, or perhaps wrapping around on itself through topological connections that make it finite yet boundless. Either way, there appears to be no wall, no discontinuity, no point where space simply ends. The cosmos continues beyond our horizon, whether into infinite vastness or into regions that eventually connect back in ways that make the question of total extent more subtle than simple finiteness or infinity would suggest. These two descriptions do not conflict because they refer to different concepts. One describes the limits of observation and causality from our particular location in space and time. The other describes the fundamental extent and structure of space itself. The boundary of the observable universe is a horizon, a limit of information rather than a physical edge. It is determined by how far light can travel in the age of the universe while space expands, creating a sphere of observability around every point where an observer might exist. Beyond this horizon lies more universe, exhibiting the same fundamental properties and following the same physical laws that govern the space we can see. Galaxies form, stars shine, and structure evolves according to the same principles of gravity, nuclear physics, and thermodynamics that shape the cosmos within our view. The difference is simply that information from those regions has not yet had time to reach us, or in the case of regions beyond the event horizon, can never reach us given the accelerating expansion driven by dark energy. The edge you can see is a consequence of living in a universe with finite age and finite light speed. Every observer occupies the center of their own observable sphere, seeing a cosmic horizon extending in all directions around them. Your observable universe overlaps substantially with the observable universes of nearby observers, but differs increasingly for observers at greater distances. Somewhere far beyond your horizon exists an observer whose observable universe barely overlaps with yours, seeing galaxies and structures you will never observe, just as you see galaxies they cannot access. This multiplicity of horizons, with each observer surrounded by their own sphere of observability, demonstrates that the boundaries in cosmology are not boundaries of space, but boundaries of perspective. Space itself continues uniformly in all directions, but what can be observed depends on where and when you are making the observation. The edges are not features of the universe, but features of our relationship to it, determined by how long light has been traveling and how much space has expanded during that travel. The possibility of infinity adds another layer to this understanding. An infinite universe would mean that no matter how far you could travel, no matter how long you continued in any direction, you would never encounter an edge or boundary. Space would simply go on, filled with galaxies and cosmic structures extending without limit. The number of stars would be infinite, the number of planets infinite, the number of regions similar to our observable universe also infinite. Every possible arrangement of matter within the constraints of physical law would occur somewhere, infinitely many times, scattered throughout infinite space. Yet even in an infinite universe, each observer would see only a finite portion, bounded by their own horizon. The infinity would remain forever beyond observation, a mathematical property of space's extent, rather than something that could be directly verified. We could infer infinity from the measured flatness of geometry combined with theoretical understanding of how flat space must extend, but we could not see it directly. The infinity would exist beyond the edges of observation, unreachable yet fundamental to the cosmos's true nature. The distinction between edges and boundaries, between observable and total, between finite observability and possible infinite extent, represents one of the deep insights of modern cosmology. The universe proves to be more subtle than everyday intuition would suggest, with properties that require careful thought to understand properly. The edges we measure are not walls, but horizons. The infinity we infer is not visible, but structural. The boundaries exist in information and causality rather than in space itself. Understanding these concepts changes how we think about our place in the cosmos. We exist in an observable bubble of finite extent, able to see approximately 13.8 billion years into the past, and to distances stretched by expansion to approximately 46.5 billion light-years. This is our cosmic horizon, the full extent of the universe we can access through observation. Beyond it lies unknown territory, possibly infinite, certainly vast, filled with structures and patterns we will never see, but which nonetheless exist as part of the same cosmos that we inhabit. The future will bring improved observations that may narrow the range of possibilities for what lies beyond our horizon. Better measurements of cosmic geometry, more sensitive searches for topological patterns, deeper understanding of the physics of inflation and dark energy, All these might constrain our models and perhaps rule out some scenarios. But the fundamental limitation of observability will remain. We can see only as far as light has traveled in the age of the universe, accounting for expansion. Anything beyond that distance, no matter how real, remains beyond our direct access. This limitation is not cause for frustration, but for wonder. The universe reveals itself as something grander than the portion we can observe, extending beyond our boundaries of measurement into realms that challenge imagination. Whether infinite or finite but immensely large, whether simply connected or topologically complex, the cosmos demonstrates an extent and structure that exceeds the observable sphere that defines our cosmic neighborhood. We live within an edge, bounded by light and time, while existing in a universe that may itself be unbounded, continuing forever, or wrapping around in ways that make the concept of edges inapplicable to its fundamental structure. The mystery of cosmic boundaries and extent represents one of the most profound questions we can ask about physical reality. The universe has edges in observation, but possibly none in existence. It is finite in what we can see, but perhaps infinite in what exists. The boundaries are real and measurable, yet they bound only our knowledge, not space itself. This paradox, which is not really a paradox but a distinction between different concepts, encapsulates something essential about the cosmos and our relationship to it. We are finite observers in a universe that may be infinite, seeing edges in our observation while existing in space that may have no edges at all. The journey through these concepts, from the observable horizon to the possibility of infinity, from particle horizons to event horizons, from flat geometry to complex topology, reveals a universe of remarkable subtlety and grandeur. The edges are there, marking the limits of light and causality. The infinity may be there as well, extending beyond all boundaries into vastness beyond comprehension. Both truths coexist, complementary aspects of a cosmos that continues to reveal itself as more magnificent and mysterious than we could have imagined. Thank you for spending this time exploring these ideas, contemplating the nature of cosmic boundaries, and the possibility of infinite space. If you found this journey through the edges and the beyond meaningful, I invite you to like this video and subscribe to Nebula Nights for more calm explorations of the universe's deepest mysteries. There are many more cosmic questions waiting to be examined, many more concepts that challenge our understanding and expand our appreciation for the vastness and complexity of existence. I hope you will continue this exploration with me.